Okay, thank you. Hello everyone. I'm Barış Güner from Recep Tayyip Erdoğan University, Rize, in Turkey. The title of my presentation is The Magnetic Levitation and Triple Field Performance of Multi-Seeded YBCO Samples with Triangular Arrangement. And these are our collaborations from Karadeniz Technical University, Dr. Abdioğlu and Professor Öztürk, from National Cheng Kung University, Taiwan, and from Sinop University, Professor Çelik. And firstly, the way of my presentation is like that. Firstly, I would like to say that about single grain. Okay, I would like to go on. I would like to say that about single grain superconductors, and the fabrication technique is the top-seeded melt growth process and magnetic levitation force measurement system and threshold field measurement systems. Why large single grain? Because there is a good relationship between magnetic levitation force and triple field and critical current density, and also the radius of the current loop is very important for our triple field and magnetic levitation force measurements. So why not multi-grain? Because weak link nature of high angle grain boundaries and small current loops causes the low triple field and the low magnetic levitation force. So the bulk superconductors, we generally work, or we generally study the YBCO single grain superconductor and gadolinium barium copper oxide single grain superconductor. And YBCO, it's a composite, and YBCO Y123 superconductive matrix and Y211 non-superconductive matrix, and also. So the size of the superconductors reach large, a few centimeters, and it has high critical current density. And also there are many useful applications such as flywheel bearing systems, high magnetic field permanent magnets, and levitated transportation systems. So, and I would like to say some things about the top-seeded melt growth process. So, firstly, we choose the seed. Seed is very important point, very important parameter for top-seeded melt growth process, because the growth process by using the seed. So YBCO must be includes superconductive powder Y123 and non-superconductive powder Y211. Y211 powder sometimes we use the green phase. So the seed characteristics is very important. So the peritectic temperature must be higher than YBCO. So sometimes we choose the neodymium barium copper oxide or samarium barium copper oxide seed crystal for GIPCO. So the seed characteristic must be similar lattice structures. It's very important, and for triangular phase, for these seeds must be similar lattice structure like mirror, and also it must be higher melting point. So And then we have to use the cerium oxide powder, because cerium oxide powder was added to prevent the grain growth of Y211 phase. We before works we studied the behavior of the cerium oxide powder. So when we add the optimum cerium oxide powder, we can uh, fabricate good single grain YVCO. So the peritectic solidification is like that. During the Tmax, or the maximum temperature, Y211 and Y123 and cerium oxide combine to go to goes to the good single grain micro. So as I said before, the peritectic temperatures is very important. And how can we find this peritectic temperature? We use the DTA graph, and when we analyze this graph, so we choose we use these points, and for example, we choose the 1,000 centigrade degrees, but this centigrade degrees is changeable, because each furnace has a different thermal process. So this we have to try to optimum peritectic temperature. Of course, this centigrade 1,000 centigrade degrees is optimum for YVCO. So this the view of the top base of YVCO pellet before thermal process and after thermal process, like that. So this process this belongs to the top sealing melting growth process. During the Tmax, our samples like that. During the peritectic temperature is like that, a small growth, can you see? So this one is the during the between TG1 and TG2, and after the thermal process, and like that. So these figures the triangular seeded Yipko samples, and we choose the seeds, the same seeds, and also the seeds grain junction is the parallel, like that, and we change to the D between this distance between these seeds. So we use these seeds, and then we change to the E distance, and also we obtain these samples. And the diameter of these samples is 32, but B14, the diameter of these samples is 40 millimeter. And then I would like to say that some are magnetic levitation force measurement system. This system is in the Cardenas Technical University, and we can measure the magnetic levitation force by using different permanent magnet waves. So for these samples, we choose these magnetic flux density distribution of permanent magnet guide waves, because this is before the works we choose the optimum permanent magnet guide waves for our samples. So just 1 second. And also this one is the levitation force measurement movement, and also this one is the for guide wave. guidance force for magnetic levitation force systems. So, for our samples, we changed the d distance. D0 is the, as I said before, this single grain. D6, the d distance between the d seats, and so triangular shape. So D10 is again the d distance, and this samples is different than this one because we choose this one. Why? Because this D14, we wonder the so the behavior of the or also uh, the distance behavior because next slide I would like to say that about the seat distance and also so when we analyze these graphs and also D14 of course must be high levitation force for this one. This is the 50, 55 Newton. So the D14 and then we choose the D0 because this is a high superconducting flow must be higher than D6 and D10. So when we analyze the cooling rate is 10 millimeter. Again, this is a systematic behavior between these graphs. So when we analyze the guidance force, again we obtain the same behavior for this graph. When we analyze this graph, again D0 is higher than D6 and D10. So this is a systematic behavior for these samples, and also we uh, we so we measured the tripled field in National Cheng Kung University. These collaborations, these scientists are our new collaborations. So we obtained the system, both magnetic levitation force and ripple field behavior for these samples. Again, for example, the amount of the ripple field is 2 kilogauss, like that.
Sorry.
And then
3 minutes, please.
okay. Again, when we analyze this one, again the amount of the triple field is decreases D6, and then again this the amount of the triple field increases the D10 and also again this D14, the amount of the D14 is decreases because when we choose or when we see the D14, there is a not good growth on these pictures. Maybe later we can analyze the scanning electron microscope or EDS analysis. We can analyze this behavior later. So this is a very important point for this graph. So as I said before, the amount of the magnetic levitation force and triple field is higher than the D6 and D10 because these dotted black circles, this one, so the around to the seed circle. So the blue circles, the this one. So circulate inside this one. So each grain inter-grain torrents. When we analyze the triangular shape, each seeds the circulating or intergrain supercurrents. For example, for the dotted black circle, intergrain supercurrents like that, and then this dotted super currents decreases for D6 and D6, and then we increases the D distance for D10, and then the for the dotted black circles is higher than 6, and then there is the systematic behavior for triple field and for magnetic levitation force. And then the when I see this one, and then the total of the supercurrents is higher than for D10. So this is and also for the 14, the total of the total of the supercurrents is higher than for D10 and D16. And so thank you very much for your attentions, and that's all.
Thank you very much. Well, I have a small question because I know with these kind of samples, one of the biggest problems is oxygenation. Have you find any difference when you make the oxygenation treatment about the cracks on the samples? Difference between the single seed and triple seed?
Of course, the oxygenation is very important point for. We use the 450 centigrade degrees, but the flowing oxygen, and also for example, there is a problem. For example, if the oxygen tube are finished during the oxygen process, in the sample, there is a non-oxygen points in the samples, and then these points causes, as you said before, the cracks, and we unfortunately we can't test the structural properties, and during the SAM analysis we can test it, but we unfortunately we can't test by using SAM analysis.
Okay, thank you.